Hello and welcome to the second lecture in the course 1DV507. Today, the topic for today is recursion and external packages. This is a rather strange lecture. They are not related in any way. Recursion is a way of thinking, I would say, a strategy for how to solve certain problems in a neat and elegant way. External packages is just a technicality. How do I download a package from the internet and start making use of it in my programs? I think this is a funny lecture. Recursion is fun, I think. Usually the student either hates it or likes it. It depends on, and I don't know what it depends on, but certain students have often problems with recursion. It's a new way of thinking, and if you're not used to it, it might take a while. And for a certain student, it might take a very long while before it starts to feel natural in any way. So we will talk about recursion and recursive methods, and we will talk about external packages. I will show one concrete example of how to use an external package. I will put together a very small Java program that can play MP3 tracks. And this is a typical exercise for when you are using external package. You have a problem you would like to solve. You are sure that someone has solved this problem before, for example, playing MP3 tracks. Then you Google a bit, and then you find a suitable package. You download it, install it in Eclipse, and start to use it. Reading instructions for today are 13.1 to 13.5. So we start with recursion. What is recursion? There are two ways to answer this one. Well, I say a way to think when creating algorithms and solving problems. And also, when it comes down to the facts and implementation, you will see that in 99% of all cases, it means that the method calls itself. We solve a problem by having a method calling itself in a loop in some way. Is it important? Yes, I think it's very important. Certain problems are much easier to solve using recursion. Later on in this course, we will talk about binary search trees, for example, and they are basically impossible to solve without recursion. You can solve them in theory if we can do it without recursion, but it's very much more difficult if you don't are using recursion. So certain problems that you are facing as a programmer are best handled using recursion. Is it always good? No. In many cases, iterative solutions are just as good. In certain cases, recursion is bad. I will show the Fibonacci sequence and the computation of Fibonacci numbers, that this one is very costly if you have a recursive approach. Is it possible to solve more problems using recursion than without? Theoretically speaking, no. Everything that can be solved using recursion can be solved without using recursion, but it's much, much harder in certain cases. It is not from a theoretical viewpoint necessary to use recursion, but in practice it is much easier to use recursion in certain cases. I will start with a very simple example. Sum up to n. Sn means that we are summing all the values from 1 up to n. That means we are computing this sum. Do you understand this definition? Sum of n is this one. If you were asked to implement this, you would probably come up with something like this in your Java program. You would say that the sum initially is 0, we have a counter starting with 0, and then we are repeating the same process n times. We are updating the counter and we are adding the new value to sum. Do you agree that we are computing the sum 1 to n in this case using this algorithm? Yeah? We are just count takes the value 1 the first iteration, 2 the second iteration, 3 the third iteration, and we are just adding them together, so we are computing this sum. Another way of expressing exactly the same problem is to compute the sum in terms of a smaller sum. So this first terms here, if I skip this one and take the n-1 first term one, then this one is equal to the sum of 1 up to n-1. Do you agree? So I can say that the sum up to n is the sum of up to n-1 plus just n. Yeah? This is the recursive formulation of the problem. We are solving the problem in terms of solving a similar but smaller problem. We can say that if we only can solve this problem, and then solving this problem is done in this simple way. So recursion, not always, but very often it means that we are facing a problem and we are describing a way to solve this problem in terms of solving a similar problem which is somewhat smaller. So if I would like to compute sum up to 5, I would say that this is the same thing as just the sum up to 4 plus 5. And then I can say, okay, how do I solve this one? Well, I solve it like this, and I solve this one like this, and I solve this one. The problem so far is that we don't know where to stop. We must in some way introduce something called a base case, a case where it all stops. Do you have any suitable base case to recommend me here?
1.
Sum of up to 1 is equal to
1.
Yeah. We need to insert a stop condition. It's called a base case. So arithmetic sum can be expressed like this. If I would like to compute the sum up to 1, then I know that it is 1. Otherwise, I compute it in this way. This is a complete definition that is similar to the one that I showed earlier on with the sum sign. It contains the same information. It contains, in the end, the same computation as well. It's just another way of expressing how we are solving this problem. Does it make sense? Sum up to 10. It is the sum up to 9 plus 10. And then we are attacking sum up to 9, and we are using the same rule again and again until we reach the case sum up to 1. Then we know that this is a fact 1. It stops the recursion. So if I should describe it as an algorithm, rather than iterating n times, I can do it simply like this. If n equals 1, I'm returning 1. Otherwise, I return this computation plus n. This will solve the problem. If you implement this in Java and you give it 100, it will solve the problem for you in just a few lines of code. Does it make sense? What happens? Assume that I would like to compute the sum up to 5. I'm calling arithmetic sum, recursive version of it, with 5. Then this one will call arithmetic sum with 4, which in turn will call it with 3 and 2 and 1 until it stops. So it will stop when we are reaching n equals 1. It will start to return 1. So this one, the base case, we are calling, starting by this one, which calls this one, which calls this one, and we reaching the call to the version with 1 as our input. This one returns 1. And then we are back in this method. It takes the result of the call plus 2. This one takes the result of the call plus 3, the result of the call plus 4, the result of the call plus 5. So in the end, we will return 15 here. So at one point in our computation, we have started 5 different calls. We have started this one, we have started this one, we have started this one. So at one point, we have 5 calls that have started but still not completed. then we are completing the last call, the second last call, and so forth. Do you understand how it works? Good. So, recursion. Compute a solution to a problem using a smaller but similar problem. In general, we have a method calling itself. In order to not be trapped in an infinite loop, we must have a base case that stops this call sequence. As I said earlier on, if you can do it recursively, you can also, in theory, do it without recursion. But you will see that there are certain cases that it's much, much harder. I don't know how to solve them without recursion. They are common in both mathematics and in computer science. Recursive definitions. I will show a few examples of recursive definitions. For example, factorial, very similar to sum. You have seen this exclamation mark computation. 5 factorial means 5 times 4 times 3 and so forth. I can define it like this. The factorial of 1 is 1, otherwise it's computed as n times a smaller factorial, like this. It's very similar to what I did for the arithmetic sum. A palindrome. I'm introducing here something called a simple palindrome. A text is a simple palindrome if it is the same text when I'm reading it in reverse. So for example, Anna is a palindrome, since if I'm reading it in reverse, it has the same sequence of characters. Madame, all these are palindromes. A recursive definition of a palindrome would then be to say that an empty string is a palindrome. A string with length 1 is always a palindrome. A string is a palindrome if the first and last characters are equal and all characters in between is a palindrome. Does it make sense? I have a sequence of characters here. If this sequence has the length 0, it is by definition a palindrome. If it has the length 1, it is also a palindrome, because it's obvious that reading them backwards it will be the same one. Then I'm saying that this is a palindrome. If this is a palindrome and P and Q here are equal. If they are equal and this one is a palindrome, then this one is a palindrome as well. Does it make sense? So this is a perfect definition of what I mean by a simple palindrome. I have given the base cases here and I've given the so-called inductive case here. How I can check that something is a palindrome based on a smaller problem, checking that the interior part of it is a palindrome. Does it make sense? Good. Once you have a recursive definition, implementing them is in many cases straightforward. For example, the factorial case, I would like to compute the factorial for the number n. I say that if n equals 0 or 1, I return the value 1. Otherwise, I say it is n times the factorial for a slightly smaller problem like this. And this one will compute the factorial for any number that you're providing, any positive number that you are providing. I will also introduce a new concept, indirect recursion. A method that calls itself in several steps. For example, I have a method A here that calls B, and inside B we are calling A. Then in 2 steps the method is calling itself. It's called indirect recursion. It's tricky. We will not use it. It's not necessary in this course, but trying to solve problems using indirect recursion requires a bit of thinking, I can say. And basically, looking at code where people are using indirect recursion is difficult to understand the code in general. But it's called indirect recursion when the method is calling itself in several steps. This is palindrome implementation. I said that a string, a character sequence, is a palindrome if it was the empty string, a string of length 1, or if these guys were equal and this one is a palindrome. So I can check it like this. We are inserting an array here, and we are starting the problem by giving 0 here and the length of the array here, the final position of the array here. If this condition is true, it means that we have the 0 length string, we have the empty string or the string of size 1. Then we said that we should return true. This was the base case. Otherwise, if the first and the last character are not equal, then we can return false. We know that it's not the palindrome. And then we ask, okay, then check the remaining ones. So we are sending in the string one more time, and we are moving P here, and we are moving P here. And it will repeat the same process. It will check, is this the empty string or a string of length 1? No, it's not. Are they the same? If they are the same, then we might go on and check the smaller problem here. If they are not the same, P and Q, we will return false and say that we don't have a palindrome. If I didn't call it is palindrome and gave you this code, would you be able to figure out what it's doing? After a while, maybe. It is, when you are not used to it, recursion looks a bit strange. But you will see that the solutions like this one, they are often very short. If you come up with a clever idea, you can solve problems in a very compact way. So, if I would apply this algorithm on Madame, then I would start by saying is palindrome Madame and the first position and the last position in this string. In general, start in 0 and word length -1, like this. So, recursive methods, one or more base cases where simple results are given directly, explicitly, one or more inductive rules where larger results are expressed using smaller results. In this case, this is the inductive step. And this is the base case up here. Do you have paper and pen? Please. I will give you a few small problems here that are related to. I would like you to write down the Java code for a method called fib that computes the nth number in the Fibonacci sequence. The Fibonacci sequence is a very simple mathematical sequence. Every number, the first number is always 0, the second number is always 1, and all the remaining numbers are the sum of the two previous numbers. So 5 is the sum of the two previous numbers. 3 is the sum of the two previous numbers. 34 is the sum of the two previous numbers. What would be the next Fibonacci number here? 89. You take the two previous numbers, add them, and you have a new number. 89 here. Please write down a recursive method that computes the nth number in the Fibonacci sequence. For example, fib6 should give 8. Okay. I've started a bit here. If n equals 0, what should we return in this case? If n equals 1, we should return 1. In all other cases, what should we return? Yeah, we should return the two previous numbers. Oops, fib n minus 1 plus fib n minus. This is it. It is basically exactly the definition as I put it. The first one is 0, the second one is 1, and the remaining ones are the Fibonacci number, the two previous Fibonacci numbers. So the Fibonacci number for n in most cases is the Fibonacci for n minus 1 and the Fibonacci number for n minus 2, the two previous numbers. Of course, if we are calling this one with Fibonacci 5, we will end up with Fibonacci 4 and Fibonacci 3, which will branch itself into a large number of different Fibonacci calls. But in the end, all these sequences will end up here and here. And we will compute the result returning back from these calls. Yeah? How many of you did put down this one? Ah, good. Good. Another example, recursive method mult, A and B, that computes the multiplication A times B with only the use of addition. You are not allowed to use multiplication. So it should be a method public int mult int A int B, and then not much code, a bit of code in here. Also, I said that you can assume that both A and B are positive, larger than 0. You can start by thinking A times B. How can you rewrite this so we are solving this problem using a simpler problem with multiplication, a smaller problem? Well, it is equal to A plus B minus 1 times A. A times B equals A plus B minus 1 times B. Now you should just implement this ID. What should I write up here? If B equals 1, we should return A. Otherwise, we should return A plus mult A times B minus 1. Like this. We have solved the problem in terms of a slightly smaller problem where we have reduced the size of B. And we are continuing like this. We will eventually reach the case where B equals 1. And we know that case. Yeah? A final one. Write a recursive method print. Print in the content of, well, it should be A here or A, of this array, starting from position 0 and onwards. And if you, once you have solved this, you can think about it, how to do it in reverse. But it should be a recursive method. Print int array R and int n. For example, you have created your array. R here. You have created it in some way, and then you are calling this method just by saying print R, and you start it by inserting 0 as the first here.
Shouldn't it be void?
It should be void. Very good. If n equals R length, or not equals R length, what should we do then? One time?
System out print and then A or array of the A at the point of the N,
Yeah.
and then you go over the
I take a short version here. R n, and then and then we are calling print R and yeah, system out print line. We are calling an array with 0 to start with. This is an array of non-zero length. We reach this part. Well, n is not equals to the length of the array, so we are printing the first element. And then we are calling print one more time and move one step forward. The next time we will print the second element, but finally this number will increase, so we are reaching the array length, and then we don't do anything at all. Yeah? Yes? I think you're not nodding enthusiastically here. Now, to change this code, that it's printing it in reverse, is a minor change. Yeah?
Return if it's 0.
If it is 0,
Return, just return. We don't need to print.
if it's 0, I don't understand. Another idea that I understand. Did you have an idea? I could start by submitting the final position, and I can print it, and I can have this n minus 1, and only do it as long as n is greater than 0 or equal to 0. Well, but what about if I'm just changing these two lines? I replace the ordering of them. I print start by 0. I will immediately call without printing with number 1, with number 2, and I will, without any printing, I will reach the stop condition. Then I will print the final call. So on the return, I will print them then. This will reverse order. If I'm only changing the ordering of these two lines, it will be reverse printing. You pointed out another solution, but I think this is a good example. It requires you to think recursively here in order to understand what goes on. You see it in your head? Yeah. What?
We used it once in the GCD test when we needed the GCD
G?
common divisor, greatest common divisor in the test, in one of the assignments.
Okay.
We used this case to calculate.
Okay, was it recursive? Yeah, it was. It was recursive. Yeah. Yeah, so you're probably seeing recursive solutions earlier on. But for most people, recursion takes a bit of practice. You don't start to think about recursive solution. In the beginning, we will often point out here, recursive solution is a suitable approach here. And in certain cases, as I will show, we will force you to use a recursive solution, like in this case. Although it's not the optimal solution, it is. If you just want to print the content of an array, it is much simpler to have a for statement and print them. This one is not more efficient, it's probably slower. But it's a good practice. Have you seen this problem? Tower of Hanoi. I received it as a kid from my parents, and they thought that it should make me smarter. I lost a few of these guys, and I broke all the rules all the time, so it didn't help me in any way. The problem is to move the dishes from one pole to another. You can only move one disk at a time. A larger disk cannot be placed on a smaller disk, and all disks must be on a pole, except for the one that we are currently moving. This final rule here is, of course, that you cannot take this one and put them somewhere here, and then move this one, and then put them on the top like this. Have you tried it? It's rather tricky. It takes a bit of time in order to solve this problem. However, you... What?
You have to do it there and go forth and...
Yeah. If there are 7 dishes, it's rather tedious also to solve it. It's a lot of moving the dishes. But anyway, the algorithm for solving it is to say, okay, start by moving n-1 disks from the start pole to the help pole, the intermediate pole. Then move the lowest disk from the start to the end pole, and then move these guys from the help pole to the end pole. It looks trivial. It says that, okay, I would like to move this one over here. Then I take the first 3 here and move them over here. I take the final one, move it over here, and then I take the 3 ones here and put them over here. The thing is that you should interpret this as a recursive solution. you should, okay, how do I solve this problem? Well, I'm moving n-2 disks from the help from the start pole, and you should apply it in smaller and smaller steps. The implementation of it is just these lines of code. And this is an example that you can find in the book. I suggest that you read it, but this simple lines of code is only 5 or 6 lines of code. If you provide number 7 here, you say I would like to my start pole is 0, my end pole is 2, and my temporary pole is 1. It will print a detailed instruction for you for exactly how to move each pole. And it's expressed only in 6 lines of code. It is a recursive solution. You should not think of it that we are cheating here, that we are moving n-1 as 1 like this. It's a smaller sub-problem, and we apply the same algorithm to solve this one until we reach the case where it's only 1 disk. And then we are moving this disk. It's a good example. I think you should read about it in the book. I cannot explain it in any non-trivial case. Another problem that is easily solved using recursion, but which is difficult to solve without recursion, is to print all subdirectories of a given directory. I ask you, this is a directory on my computer or on your computer. Print this directory and all the subdirectories of this one. I solve it like this. I say, okay, this is my start directory. I have a file object, and then I'm calling the recursive method with this one as my starting point. And it prints an indented print here of all the subdirectories of this one. I do it like this. Many things here are just related to the indented printing. Depth and count are just related to the printing. The basic idea is that visit sub here is the recursive method. It takes a directory, and if this file is a directory, I ask it, give me all your subdirectories, and I'm calling the visit sub on each one of them. So I take my starting point, this directory, and inside this method I ask this directory, give me all your subdirectories, and then we are visiting them the same. It will start visiting all the subdirectories one at a time. It will stop when the file is not the directory. Then it will stop. And if it finds a directory containing no other directories, this one will always be false. So then we will stop this one. Yeah. Print dir here. I am keeping track of the depth. I start with the depth 1. This is the start directory. And every time I go down into a new directory, I'm increasing the depth, and then I'm decreasing the depth here. And the print method just adds an extra indentation for each depth here. So it just see what is the depth in my visited in subdirectories. If it's 3, it will start by printing 3 of these guys before it prints the directory. So this is just to get the indentation here. The key part is, if it is a directory, give me all your if it is a directory, print it, and then give me all your subdirectories and visit them and do the same thing here. And this one is available on the course website. I suggest that you go home and you try to make it work. You point out one of your directories that contains many other directories. And then you should try to solve it without recursion. It is very difficult. Because when you start there, you have no idea the depth. that you have to implement. So it's difficult to solve without. It's the same way as the towers of Hanoi, very difficult to solve without recursion. The Fibonacci numbers. This one I outlined on the whiteboard. I said in order to compute the nth Fibonacci number, we check if it's 0, we return 0. If it's 1, we return 1. Otherwise, we compute it in terms of two smaller Fibonacci numbers. Do you remember this one? Yeah. Okay, this is my implementation. Nice looking, short and compact, I think. And then we have a problem. Print the first 100 numbers in the Fibonacci sequence. Easy. I iterate from 0 to 100 and I print first number 0, then number 1 and then number 2 and then I print them all at the time. If you try to do this with this implementation, your program will, your computer will start to make a few sounds and then it will die. Yeah, it is not harmless. It is harmless for your computer, but you can feel that it's not happy. What is the problem here?
We are doubling the calculation every time. We are double. So 100 doubles.
Yeah. For example, to compute fib5, I need to compute fib3 and fib4 and fib4. So in order to compute fib5, at one point I have 15 calls running at the same time. 6, then I have 25 calls running at the same time. If I am fib100, an enormous amount of calls at the same time. You can show that the number of calls that are executed is proportional to 2 raised to the power of n. And this mathematical function, it explodes. So your computer will run out of memory. At one point it will have a very large number of calls running at the same time and it will not have memory enough to keep them. So although recursion often gives nice solution, you should be afraid when you are splitting the problem into 2 new problems. If you solve a problem in terms of 2 smaller problems, you will have this situation. It will explode in the number of smaller problems. It will work fine up to 10, 15 or something like this, but just remember that it's exponential growth in the number of method calls. And it will soon run out of memory. If it is a recursive problem where we are splitting the problem into 2 smaller problems, it might explode. So recursion often gives a nice looking solution, I think. At least for me, if I come up with a recursive solution, I often feel a bit proud and happy in general. Because they're often good looking, but you should be aware that only in a few cases it is actually better than the iterative solution. In many cases, the iterative solutions are simpler and just as fast. A better solution. How do you solve Fibonacci numbers without? Well, I say that the first one is 0, the second one is 1, and then I start to iterate here and say, okay, I know the 2 previous ones, and I compute the new one. I print its result, and then I say, okay, the second previous one is now the previous one, and the latest one is the previous one. I move 2 steps forward, and then in the next loop, I'm computing a new one. This one is non-recursive. It will run perfectly fine. Then we are facing another problem here. This number, the Fibonacci number, starts to grow very fast. So actually the problem here is that we cannot longer fit them in a long. The the number is so large that the next number here, 90, gives an out of range exception or whatever it is. You cannot, it doesn't fit into a long any longer. So I could only compute the first 89 Fibonacci numbers using this approach. But the speed is not the problem. It goes very fast and zoom, then it dies. We are out of space for the long here. How do you solve it?
Big integer maybe?
Yeah, we have a class in the Java library called Big Integer. It is designed for this type of problems. When long is not enough, you should take a look at this one. This is a class, it's not a primitive type. And it's designed to handle any size of integers. It is extremely slow, because they are keeping track of any sequence of digits and consider them as an integer. And then it do operations on this one. But I could say that the first two big integers are 0 and 1. And then I say that the next one is first one added to the second one, and then I do the update. And this one will work. It will print the first 100 Fibonacci numbers for you. So the lesson here related to Fibonacci number is that recursion gives a clean and nice looking solution. Basically the definition of a Fibonacci number, you're just inserting it into the code and you have a working recursive solution, but it will give you problems due to memory. So be aware when you have a problem that you are dividing into two smaller problems. It might cause you situations like this. Assignment 1, we have 3 exercises related to recursion. One of them is to print the nth line in Pascal's triangle. This is Swedish. Line 1, line 2, and so forth. What will be line 7? Yeah, you see the pattern here is that any internal numbers here, any internal numbers, they are the sum of the two above them. So 10 is the sum of 6 and 4. 5 is the sum of 1 and 4. So you will have 0 here, you will have 7 here, you will have 21 here, you will have 35 here, 35, 21, 7 and 1. So given the 6th line, it is possible to compute the 7th line. So you start with the first line. That is your base condition. If we want to have the first, the 0th line of Pascal's triangle, you know the answer of it. Otherwise, you can compute it in terms of the previous one. So it's a recursive solution. Yeah? So, do you like recursion? Are you eager to start solving problems? Many of you, I guess, will go back to the previous course and try to solve all the problems recursively. Every time it is an iteration, you can probably solve it recursively. But you will at least get 3 opportunities on this assignment to use recursion. Anyway, at first glance, recursion solutions to problem can seem difficult, mainly because you are not used to them. You are starting, I hope at least you have started to be familiar with iterative solutions. Every time you have an iterative solution, you can probably find a recursive solution. It's just you are used to this approach. With a bit of practice, you will be able to handle this one. Many students think that recursion has a mathematical feel to it. And yes, it is true. In mathematics, we often have recursive definitions of things. There is a well-known tool from mathematics. So I think you should see it as yet another tool that is very suitable in certain problems. In the beginning, we will help you to say that this problem is suitable to solve using recursion. But later on, you will hopefully see it as one opportunity to solve a problem. Also, remember the Fibonacci case. It doesn't always run faster. It doesn't always work better in any way. In certain cases, it is much simpler, but it's seldom that it's better in any computational way. It's not faster, and then it's not, in certain cases, it's even worse. Oh, let's take a break for 10 minutes. Okay, let's continue this lecture. We talked about recursion in the first half. Now we will jump to something completely different. I will talk about how to use external packages in your Java program. But first of all, I would like to tell you one thing that I think I've told you earlier. Have any one of you tried to execute a Java program using the terminal window? How many of you have tried? Did it work? Okay, if you try, if it works, for example, assume that we have a program called argsmain in a package graphics 5, and I would like to execute this program using the terminal window. What I have to do is to move to this directory, move to the directory containing the graphics folder. So in Windows and also in Mac, you're using CD, change directory, to move from one directory to the other, and you find this directory, and then you are writing Java C graphics 5 argsmain. This will compile the program. It will take your Java code and translate it to something called bytecode. The Java file will be it will not change the Java file, but it will pop up a new file called argsmain.class. This is the result of the compilation. It is the same program as this one, but using in bytecode rather than in Java. Bytecode is the one that can be handled by the Java virtual machine. So this is not an executable program. This, the result of the compilation, is an executable program. So first you have to compile it using Java C. Then in the next phase you want to execute it. Then you're writing Java, graphics 5, and then any parameters you're interested in. If you have set up your Java installation properly, it will then execute this program, and whatever output the program is giving you, it will be displayed in the console. Have you tried it? I think you should do it. In order for this to work, there are certain things you must have done properly. You must have installed something called a Java Development Kit, JDK, and you must have configured two variables in your operating system called environmental variables, one called path and one called class path. So your Java installation, all operating systems that I'm aware of at least, they come with something called a runtime environment. This is enough Java to run a program, but you cannot develop Java programs, you cannot compile them. That means they come with a virtual machine and the class library. These are the two things you need to run a Java program. Any operating system, at least Mac and Windows, when you are, they are both comes with a runtime environment. If you would like to develop your own code, you have to download something called Java Development Kit, JDK. Apart from these things, it also comes with a compiler. That means you can convert your Java file to bytecode before you are executing it. If you are interested in Java, if you do a lot of development, some people would like also to download the API documentation. It is available online, but you can download it and have it on your computer. You can also download the entire source code for the library. It is freely available. And sometimes it's nice to take a look at it to see how the professionals are doing it. And you will see that they are, in many cases, it's not a miracle what they are doing. For example, the ArrayList class, you can read it, and it's not any fancy things in the ArrayList class. So in order to do any type of Java development, you need to install this one. Do you have it? Otherwise, you wouldn't be able to write any Java programs. Which version do you have?
1.8, I think.
Yeah. Current version, I looked it up yesterday. The latest version is 1.8 update 65. They are, every second year they are updating these ones, but then they make small bug fixes called updates of it. We are using Java 1.8 in this course. What about Eclipse? What is Eclipse? Yeah, Eclipse is a development environment. It simplifies developing Java program. It doesn't come with a virtual machine. However, it comes with a development kit. So if you're downloading Eclipse, a part of the download will be this one. But you can download this one separately. But the compiler and the Java virtual machine, they are not considered to be a part of Eclipse. They are used by Eclipse, but they are not a part of Eclipse. Okay. Assume that you would like to compile your program, then sometimes you can get something like this. Java-C is not recognized as a command operable programs or batch file. It means your operating system don't know what you mean by Java-C. You have downloaded the JDK, but the operating system is not aware of it. Then you will have to find a variable called the path variable. In Windows, you go to Control Panel, System, Advanced Environmental Variables. There you will find one variable called path, and you must point out this library in the JDK. This one library bin, it contains this program. So by adding this library to the path variable, you're making the operating system aware that we have a program called Java-C. So if this one doesn't work, you must do the following things. Later on, I will show an example using MP3, playing MP3. And you are compiling the program that is using this external library. Then you might find an error message that looks like this. Package Java Zoom Player does not exist. The compiler is not aware of your external library. By default, the compiler only knows about your code and the Java library. If you have downloaded some other package, the compiler is not aware of it. In order to make the compiler aware of all the source code or all the Java, the libraries that you are using, you must take a look at the variable called class path. It's in the same position as the path variable here. You have to add the new library to it. A class path is where the compiler looks for code that should be a part of your program. I think you should take a look at these variables. In Windows, you can find them in this, okay? If you have a Mac, where do you find these variables? Inside your home directory, you have a hidden file called bash profile. .bash profiles. In order to see it, you must write ls-a. Then you will see a file called bash profile. You can open it, it's an ordinary text file, you can open it with a text editor, and there, this is the correct place to add paths like this and this one. You have been able to run your program so far. The thing is that you are using Eclipse, and when you are installing Eclipse, Eclipse is updating all these files. They are adding class path, they are adding path variables, and fixes everything for you. But I think it's a good practice to try to execute your programs without using Eclipse. Especially if you're using an external library, then it's a bit tricky to configure it in such a way that Java is aware of your new external library. The purpose of this very simple example is learn how to use external packages. I had an idea that I would like to write a small Java program that is playing an MP3 track. Java don't have any support for this. At least it didn't have at this time when I was writing this program. So what you do is that you Google MP3 Java, something like this. You will find plenty of information. Then you take a look at this one, and I decided to use a product called Java Zoom JLayer at this one. There are a lot of different options. But what you need is a Java program that can convert your MP3 track to analog sound. So MP3 to analog Java development. If you Google on that one, you will find plenty of programs. There are a lot of strange guys sitting all over the world who do these things for fun. And they are very proud of their work, so they make it available to anyone. So Google is extremely powerful in solving certain Java problems. You Google on what you would like to do and just add Java or jar file or something like this, and you will probably see someone who has solved a similar problem and made it available to you. So I Google a bit, I find this website, and they are saying that they are providing me with the classes that I'm interested in. It was 10 to 20 classes in bytecode packed in one jar file, Java Zoom. Libraries are often packed into a jar file. It is a zip file. They have taken all the class files and zipped it into one directory, and they are called the jar file. This is the preferred way of adding external libraries to Java. Then at the same website, they showed me how to get started. I need to point out where my MP3 files are, and I decided to play the Kylie Minogue file that I have there, a legal copy of it. And then you are connecting different streams. I have to do a number of things. In the website for Java Zoom, they showed me exactly how to do this. All I have to do was to insert the name of my own MP3 file. And then I just copied their code. They tell me you should do it in this way. What you're doing here might cause an exception of type Java layer exception, so I have to catch this one. And I have it here. Oops. I found the code, MP3 main. I copied the code from the website, and then I have a few errors here. The errors here is that Eclipse is... I have downloaded this jar file and put it somewhere on my hard drive, but Eclipse is not aware of it. So it says that it doesn't recognize player, it doesn't recognize Java layer exception, it doesn't recognize anything having a package name starting with Java Zoom. You must in some way inform Eclipse that in this particular project I'm interested in these files, in this library. And it's very simple. You click on your Java project name, right-click, go to Build Path, Configure Build Path. Then you say, I would like to add a new library in terms of an external jar. I have all my jar files in one specific directory, so I have plenty of them here. But I should have Java Zoom here somewhere. I thought. Okay. I gave you access to it. In the download for the lecture today, you have the Java Zoom jar, and it looks like I didn't copy it. I moved it to this one. I can try to find it. No. We go to my Moodle. We are logging in. We go here. We go to the course. We go to the lecture today. Here we have it. I take it. Start to get a bit tricky here. Shouldn't give up this easy. Add external jar. Var? Är det den här? Okej. Okay. Find external jar. It's not in here. It is in downloads. Hämtade filer. There we have it. Open. So all you have to do, you should prepare yourself better than I do. You download in this Java Zoom jar file. You put it somewhere where you have all your jar files. And then in order to make it Eclipse aware of it, you do as I did earlier on. You right-click on the Java project. You say, I would like to add a new jar file, and you are locating it, and you are saying, open. OK. Now the errors should have disappeared. So it was only, the errors in this code was only since we couldn't find my new Java library. Now it is aware, and now we can just hopefully run it as a Java application. Yeah. So there we go. This is the general idea. You are facing a problem. You cannot find a solution to it in the Java library, in the ordinary Java library. You Google on it, and they will provide you with a jar file. That means something.jar. In most cases, this is the solution. They are delivering some package to you in a jar file. You download it, put it somewhere, and then you're informing Eclipse in this way by right-clicking on it. Then Eclipse is aware that, okay, now we do not only have the library, we also have Java Zoom as a part of our project. And all your error, then you, in almost all cases, when you're finding something like this, they have a short piece of code showing you how to get started. So you make a cut and paste and you try that it works. One problem with this package, it was very simple and it was easy to get started with, but it is that it is not a threaded application. What do I mean by that? They are not when they are playing the music, they are not creating a new thread and playing it in the background. And they are playing the music in your ordinary program. So your program stops and it blocks anything else. It stops and waits there until the melody, in this case Kylie Minogue, is completed. Then the execution proceeds. This is not good. If you want to write your own MP3 player, you would like to have it playing in the background. It must be possible to do something else with the computer at the same time as you're playing your music. But it was a simple package and it was simple to get started with. Any questions about? Let's see if I can find the slide. You will be asked in the exercises to do something similar. I think you can repeat my steps here. Try to make this program run in your computer, and that we will ask you to use a tool called Language Tool that can correct your English. I think it looks like, oops, the program looks like this, the example program. You should download a tool called JLanguage Tool. It comes with a jar file and you should be able to run this program. And this program, you have a sentence here with a number of errors. A sentence with an error in the Hitchhiker's Guide to the, it continues here. It contains a few errors. And this library that we have downloaded here, it can check this text and it will print out all the errors, and it also print out suggestions for you how to correct them. We would like you to download this jar file and make it run in your program. Yeah?
When we add an external jar,
Yeah.
is it added to the project files automatically?
No, I showed you that you're downloading your jar file and you're putting it in some hard drive. Then you must inform the Java project you're working. In your case, it might be the Java project is called 1DV507. You must add the path to the jar file to the Java project. Then everything inside the project is aware of this external library. Was it okay? So this is exercise 6. You will be asked to do something similar. We don't give you that much information. We want to like you to take a look at this website for seeing how to use this one. But in general, downloading external libraries is not difficult, and as a programmer you are doing it all the time. You don't invent the wheel by yourself. If someone else has solved the problem for you, you are downloading it and stealing their solution and reuse it. Also, later on today I will present the results for the first written exam. I was the one correcting exercise 3. Do you remember this one? Describe briefly what we mean by, and then it was a static field, and it was encapsulation, and also a compiler and Java virtual machine. You didn't do a good job when it comes to what is a compiler. Many of you answered Eclipse is an example of a compiler. It is not. And you were telling me that the compiler always translates to machine code. It doesn't do that. A compiler translates a high-level language like Java to some executable. In the case of Java, the compiler translates your Java files into something called Java bytecode .class files. These are not machine code. They are executable code, but they are not intended for any hardware. So this is the first step. Then we have the Java virtual machine. In the next step, we take our Java bytecode and give it to the Java virtual machine. This is a program that are executing your bytecode. Many of you said it takes the Java bytecode, the JVM, and translates it to machine code. No, it doesn't do that. It actually interprets your Java bytecode. It works like a CPU, behaves like a CPU, but it is not a CPU. It is a program that are reading your bytecode and doing all the instructions in there. So be aware that the compiler is one program that translates often a high-level language like Java, C, or C++ into an executable code. That's the only thing that the compiler does. It starts by checking that it is correct. And if it is correct, the program, it translates it. Then in the next phase, in the case of Java and in the case of C# as well, we take the bytecode, give it to another program. And this program is the one that is executing your code. Of course, it in some way interacts with operating system, which is interacting with the hardware. But this one is the one that works like a CPU, works like a processor, simulates a processor, and executes the code. So now you all know what a compiler is. Good. That's all for today. I will go later on today. I will go and visit a Swedish assignment group, and at that moment I will hand out the exams. Tomorrow I will visit the English group and hand out the exams for you with that. See you.